So 2.3 is zeros of polynomial functions. This is probably the most dense section in the book, so we're going to take it into several lessons. Today we're just going to focus on long division and synthetic division because it kind of comes into that, and also the factor remainder theorem, which allows you to take polynomials and divide them and know kind of what the pieces are going to come out to be. So long division, let's just kind of run through that process with you. And I always like, as a model, in case you get stuck, just do an old-fashioned elementary school kind of division problem. I like to pick one that doesn't go evenly so we can kind of think about how it would play out. So 4 going into 25, right? Well, 4 won't go into 2, so I go to the next digit. 4 does go into 25 6 times, so I put it on top, then I multiply, then I subtract, and then I see what's left. Now 4 can't go into 1, and there's nothing else to take down unless we increase decimal places, which I don't want to get into because I want to make sure we've got a remainder, so we talk about how to deal with that. So 4 goes into 25 6 and some other amount of times. And I don't know that this is maybe how you wrote it in the past, but at least not in elementary school, but this is what's going on. It's 6 1/4 times. Take the 1 over top, the remainder 1 over top of the 4 and add it to the quotient. So you have your quotient, or so you have your number that you're dividing by, and that's equal to, so you have your number you're dividing, and that's equal to the number you're dividing by times the quotient plus its remainder. And I guess that should probably be in parentheses as a, so we can distribute the 4. So anyway, that's how it would break down. That's going to end up being our quotient remainder theorem, but in a really simple elementary level way to look at it. So let's scale this up. We've got this big polynomial that's going to go inside the divisor bracket, or house thingies, what I hear a lot. And 2x squared minus 1, that's going to be the thing you're dividing by. So 2x squared minus 1 outside the house. All this stuff is going to be inside the house. Now, if you're thinking about synthetic division and whether or not that's okay, the deal is when you have when the part that you're dividing by has x to any power other than 1, you can't do synthetic division. That only works for first order polynomials. So something where it's x just to the first power. So that's why we're going to have to do long division. Synthetic's not going to work here. So over there we were looking at how many times 4 goes into 2 or 25. Really with this, all you got to look at is your leading term. So ignore this one for now, but how many times does 2x squared go into 2x to the 4th? All right, that's kind of a weird question. So another way to think about it is this. What could you multiply 4 by to get as close as you can to 25 without going over? So let's do that. What could you multiply 2x squared by to see if it come out to be 2x to the 4th? Well, if you multiply by x squared, that would do it. So one thing I really recommend is keep these things lined up by their powers. It just makes everything neater. It makes it a lot more organized as they get bigger and more complicated. All right, so now take what's on top, multiply it by the part you divided by. So 2x squared times x squared is 2x to the 4th. And then distribute it out. So x squared times negative 1 is negative x squared. And again, I'm keeping my powers of x lined up. Now I'm going to subtract. And when I subtract, what I prefer, this is kind of probably a childish way to do it, but I like it, it works. Change this to a positive and then change my other signs. Same tick, tick. I don't know, there's a few different rules or little acronyms I've learned over the years, but whatever works for you, just be careful with your signs when you're subtracting. Make sure you're good with those. So 2x to the 4th minus 2x to the 4th, that's gone. Technically, we subtracted nothing from 4x cubed, so it comes down. And then negative 9x squared plus x squared is negative 8x squared. Okay. And we can bring more stuff down at any time. I'm going to hold off on that for now, and I'm going to bring stuff down as I need to. So next piece, 2x squared times what makes 4x cubed? Okay, well that's going to be 2 times 2 to make 4. And x squared times another x to make x cubed. And then let's distribute that back out. So 2x times 2x squared is 4x cubed. And 2x times negative 1 is minus 2x. Now, I am going to bring that 2x down because it looks like it would be helpful to have that term. And now I'm going to subtract. I'm going to subtract everything, so minus, or change that to a plus, minus 4x cubed and plus 2x now. Okay, now we'll have, this will go away, negative 8x squared minus 2x plus 2x, that's gone. And I'm going to go ahead and bring down the 5 now, because I probably will end up needing it on this next step. So now, 2x squared times what makes negative 8x squared? Well, if multiply by negative 4, that should do it. So negative 4 times 2x squared is negative 8x squared. Negative 4 times negative 1 is plus 4. Okay, but we're going to subtract that term. And I'm going to change the sign so everything becomes the opposite. All right, that's going to be gone now. And 5 plus negative 4 is 1. So I've got a remainder of 1. And I'm going to put that over top of what I divided by in the first place, just like I would have done over there. And that's it. That's our quotient and remainder. So long division is a long, drawn-out process. Synthetic, if we can do it, it's way easier. It's what most people tend to go with. It's what I use when I'm just trying to get this stuff done as quick as possible. So I'm going to go through the process, kind of point out a couple little things to be aware of. I have proved this to students in the past. I don't know that most of the parts of it are super straightforward. So if you really want to see how synthetic division is possible and how it ties back to long division, it can be done. It's not super obvious, so I don't really tend to show it to everybody unless you just really want to see a proof of why it works. So if you do, let me know. So the way you're going to do this, you take the part you're dividing by, and you set it equal to 0. Now when we get into the factor remainder theorem, hopefully this stuff will make a little more sense as to why this is okay and why it works. So I'm going to subtract 1, and I'm going to divide by 2 to get the x by itself. So that's going to go in a box. The result, when I solve for x, that goes in a box right here. Then I take all of my leading coefficients, I'm sorry, just my coefficients without the variables, and list them out. So 4x cubed. I don't have an x squared, but I do need a placeholder for that. All right, now I've got 5 for x and 8 for the ones place. Again, if you need to see why this is happening, why there's a placeholder necessary, I can give you some background for that as well. Just let me know. So the process, you bring down the first term always, and then you multiply by what's in the box. So 4 times negative 1/2 would be negative 2. Here you add, and then back to multiply. So negative 2 times negative 1/2 would be 1. Add these, back to multiplying, so negative 3, and add those, we get 5. Okay, so the last part, you always start with the box, you always end with the box. And there's one more little catch here, and again, I can prove this to you if you want to see it, let me know. It's not the most straightforward thing, but it can be made to make sense. Probably better off just remember this. If you have a fraction, whatever was in this denominator, you need to divide each of these terms by that number, but not the remainder. It comes back to the fact that this factor had a 2 out front, and if we're solving for x, you need to divide that 2 off. That's a short and sweet way to put it. That doesn't really explain it, but that's where it comes from. So this is going to be a 2, this is going to be a negative 1, this is going to be a 3, and that remainder is going to stay the way it is. You don't divide it by 2. And as far as the x's that go with these, you start with x cubed, you divided x off, so this is going to be x squared, and then you count down. So 2x squared minus 1x plus 3 with no x, and then finally your remainder over top of what you divided by in the first place, which was 2x plus 1. And that's going to be it. That's going to be your quotient here and your remainder. So a big topic in this section is called the factor remainder theorem. Now you've had a problem of the week that you kind of dove into why this is working, so now this kind of ties back to that problem of the week. But what the theorem is going to show you is that if you synthetically divide a polynomial by a factor, your remainder is the y value that comes out. And we'll try to illustrate that point and show you why that's happening. So if I want to find f of 1, all right, let me shade this so I'm not giving you too many things at once here. So if I want to find f of 1, the long way about it is just plug in 1 and see what happens. And that's going to give you 1 plus 1, so 2 minus 2, that's going to be 0. Okay. So now I ask you, what is f of x divided by x minus 1? All right. Well, synthetic division would be a good way to do that. Set x minus 1 equal to 0, so x would be 1. That would go in the box. Our polynomial was 1x squared plus 1x minus 2. And now we carry out the process. So bring the 1 down, multiply, add, multiply, and then add these, and there's no remainder. So our result would be x plus 2, but more importantly, there's no remainder, and that's what I'm trying to show you. That's your y value. So really, for the sake of this problem, that's what I'm focusing on. The fact that when you divide whatever number you were going to plug in, the remainder you get out is the y value for that answer. Let's try f of 2. So I'm going to do the same process. If I were to plug in 2, then I would have 2 squared plus 2 and then minus 2. Okay, so that would be 4 plus 2, so 6, and then minus 2 again is back to 4. So we're going to do synthetic division. 2 would go in the box, and then 1, 1, negative 2 as your polynomial. So bring this down, multiply, add, multiply, add, and there's the key point right here. The result you would get when you did plugged in 2, the function is the same thing as the remainder you're going to get out if you do synthetic division. So now let's explain this theorem and why it's working the way it is. So let's let f of x be some polynomial. All right, well that means that f of x can be expressed as several factors multiplied together. Your book's probably doing this as like n1, n2, and then n sub something. I think it's just easier to see it this way, a, b, and then it doesn't mean stop at the letter n, it just means you keep going until whatever number of terms you have. So that's your function. Suppose we divide this by a. All right, so we take f of x and we divide it by a. Well, you'd have f of x divided by a here. Let's just write that out. Divided by x minus a. And that term would cancel out right here. We divide out and become 1. So f of x over a, I'm getting ahead of myself. F of x over x minus a would be all of your other factors besides x minus a being in here. So let's look at a couple scenarios. First case is a is definitely a factor of f of x, so it was a 0. If we were graphing the function f of x, a would have been across the x-axis. So let's assume a is a factor, because basically it either is a factor or it's not a factor. So case 1, let's assume that it is and see what happens. So if f of x is a factor, we get back to where we just were. F of x divided by x minus a would equal x minus b and so on, all of your other factors. So think about this. Here's the original function again. If you were to plug in f of a, well, you would have a minus a right here times all your other stuff. Well, that's 0. So 0 times anything else is going to be 0. So that's kind of the, maybe it's almost too straightforward, but if a is definitely a factor of this polynomial, then when you plug in a for x, it's going to cancel out and be 0. Your end results will be 0, which means that if a is an x value, it's the point is definitely on the x-axis because your y value is 0. Right, so now let's look at the other case, which is way more likely that a is not a factor of f of x. So that means when you plug in an x value for A, you get some other y value that's not on the x-axis. So again, that's way more likely to happen. So let's kind of see how this would play out. So let's start the same way we did in the beginning. Now, from what we've seen so far doing long division, if A is not a factor of f of x, this is how it would play out. Your x minus A over here would divide out. But then you would also have some other remainder, and it would get divided by x minus A. So again, if you need me to clarify, let me know. Hopefully I'm not blowing through this too much, but I guess real quick I'll show you this, just to kind of confirm. Your function could be written as x minus A times your other factors, and then if you multiplied r over x minus A by x minus A, you would just have your remainder. So hopefully that looks pretty familiar. Your function can be written as all the factors times each other plus whatever remainder you would have on the end. So back to the original point though, if A is not a factor of the function and we divide x minus A out, we will get a remainder, and that's the format we're going to put it in. So now think about what we just talked about right there. If you rewrote your function, this is how it would look. So let's finally find f of A in this scenario. Well, if you did that, you'd have A minus A here, which becomes 0. So that means all of this stuff that's multiplied by 0 goes away, except for the plus r. So that means that if you put in A as in your function, the final result will be r. If you think about synthetic division, if you divide by A, that's your remainder. So as far as the ordered pair, this is your x value, this is your y value. So your remainder is your y value.